Welcome to the video for chapter 28. Today we're going to be talking about what happens when transmission lines have losses. You might remember, it's possible you remember that when we were first deriving the equations for transmission lines, we assumed that they were lossless, that they had no resistance, no impedance of any sort, and so therefore the signal would propagate forever down the line. It turns out that that isn't the case, of course. In the real world, there'll be resistance on the wire. There'll be the possibility that leakage current can pass through the insulator, through the dielectric material, and that leads to a phenomenon called dispersion. And we're going to talk about dispersion. We're going to talk about group velocity, which accompanies dispersion. We're also going to talk about how we can eliminate dispersion by a distortionless line. The historical perspective today is John William Strutt, and he just looks so old-time British to me. He was the Lord of Rayleigh, and he actually discovered Rayleigh scattering. So if you remember back when you were like 3 years old and you asked your parents, why is the sky blue? It's Rayleigh scattering, and it was John William Strutt that discovered that. Of course, that's not why he's our historical perspective today. He's the person who formalized the concepts of dispersion and group velocity. So it's very relevant to realize that the stuff that we're talking about here has been around for 150 years, and that's pretty remarkable. That when we get to the end of the last section today, the punchline of the whole thing is something that happened in the mid 1800s, and so that's pretty remarkable to think about how long these things have been in place and how long people have been doing the sort of mathematics we're studying today. Okay, so you might remember that when we first introduced transmission lines, we had a model that had inductors and capacitors. And that's really all that it had. There were inductors and then there were capacitors. And we had a distributed model, so there were these units, and it was L hat and C hat. And the hat just indicates that it is per unit meter. And we can have however many blocks we want for however long the transmission line is. Well, what we're going to do now is we're going to add two more components, R hat and G hat. R hat represents the fact that there will be some resistance to current flowing down the wire, that the conductors are not perfect, and as a result, there's going to be some resistance that will prevent the current from flowing. The G hat represents the fact that the insulator is not perfect. We have the transmission line, and that transmission line has an inner conductor and it has an outer conductor, and in between those two conductors there's an insulator. Well, it turns out that there's the possibility of a very small amount of current passing through that insulator from the inner conductor to the outer conductor, or vice versa. And that's what G hat represents. Now, what we're typically going to find is that R hat is pretty low because the wire's made of copper, and copper is a good conductor. G hat is pretty low because the insulator is equally good. So these are probably going to be relatively small, but they're not necessarily negligible. And while they might be negligible if the wire were, say, 10 meters long, if the wire is 10 kilometers long, all of a sudden then these quantities are less negligible. So remember that L hat and C hat represent the parasitic inductance and the parasitic capacitance of the cable. Very frequently it would be a coaxial cable or a twisted pair. And then we have now the new additions, R hat and G hat. We've already seen, for example, that the phase velocity of the lossless line was the square root of L hat, square root of 1 over L hat times C hat. And so we'll be able to rederive that equation with with a couple of exceptions in the lossy circumstance. Well, there was a derivation that we did for the transmission line equations, and we're just going to sort of model that same derivation for the lossy system. And I'm not going to go through the steps because you've already seen the steps, and as really cool as I think it was, you probably think it's less cool and would probably think it was even yet less cool again the second time. So I'm just going to present to you these equations. I'll just remind you that these terms over here on the left, these essentially began as doing a current at Z minus delta Z and at Z, and then a voltage at Z minus delta Z and Z, and then taking the limit as delta Z goes to 0, and that difference essentially becomes a derivative. So the terms on the left are derivatives that come from taking a limit as delta Z goes to 0. Of course, C dV dt, that's the current through a capacitor, and this first equation is from Kirchhoff's current law. So this is KCL and this is KVL, and for KVL the voltage across an inductor is L di dt. And then now we have the new terms. So these two terms here are the new terms. Everything else that we've already talked about. But now these new terms are going to be added on here. That's going to make things a little bit more complicated. Again, remember that if r hat and g hat both go to 0, then those new terms are going to go away, and we're left with what we've previously referred to as the transmission line equations. Now we're furthermore going to assume that the signal is going to be time harmonic. It's going to be sinusoidal, which it almost always is. And so then we can reduce. Let me try to fit this on the page. Nope, not going to fit on the page at the same time. I'll just remind you then that this j omega c hat term came from c hat times the partial of v with respect to time. That the partial with respect to time can be represented as j omega times the variable. So the partial of I with respect to time becomes j omega L hat times I. So this equations 28.3 and 28.4, these are just simply the modified versions of 28.1 and 28.2 when we've converted into harmonic equations. Now we can define the total admittance and the total impedance of the line, where the things in square brackets for the two equations up above are the total admittance. So this is the admittance of the line, and this is the impedance. Now this is not to say, typically we find that y hat equals 1 over z hat. That's not what we're doing here, because 28.5 and 28.6 are two quantities that are both relevant to this line, but they're not the complements of each other. So that's not true in this case. We're going to then plug 28.5 and 28.6 into 28.3 and 28.4. So effectively, y hat is going to go in place of g hat plus j omega c hat, and z hat is going to go in place of r plus j omega L hat. So we now have two pretty simple, relatively simple differential equations. These require that we be in the lossy model, and furthermore, they require that we have harmonic signals. We're going to substitute equation 28.8 into 28.7. So in other words, I'm going to solve this equation for I, and then I'm going to plug that in for the I that appears there. So I end up with a second derivative with respect to I, and then a second derivative with respect to V. So depending on whether you substitute 28.8 into 28.7 or vice versa, you get these two expressions. But notice that in both cases, this is simply an expression in I, so I occurs on both sides, and everything else is a constant. This is an equation in V. V occurs on both sides, and everything else is a constant. So we can then solve those equations. Those take the form of the Helmholtz equation, just as when we were doing the transmission lines in the first place, and previously just as when we were doing the wave equation. So this is kind of the third time through seeing this. It's just that this is probably the most complex version of it. It is the most complex version of it because these are now complex numbers. But the solution to the Helmholtz equation always takes on the same form, and that is that there is the possibility of a wave moving to the right and the possibility of a wave moving to the left. And each of those can have different amplitudes, but they're going to have the same constant, and that constant gamma, and I don't know why the font shows it like that. I draw gamma like that, but the font tries to make it look more stylized. Gamma is the square root of z hat times y hat. So let me just come back up here and remind you that this is essentially saying that this is equal to gamma squared times v, and that this one is equal to gamma squared times I. So what we do is we start with the four variables. So we have g hat, c hat, r hat, and L hat. And then we also need to know the frequency. From those we can calculate y and we can calculate z. And once we find y and z, then we can come down here and use those to calculate gamma. Take the product of z times y or y times z, it doesn't matter. Take the square root, you'll get gamma, and then gamma can be broken into a real part and an imaginary part, which gives us alpha and beta. So you could think of this as g hat, L hat, c hat, and r hat. Those are used to generate z hat and y hat. Those are used to generate gamma. Those are used to generate alpha and beta. So that's kind of the workflow that we'll be following in these problems. And you could just skip right past z hat and y hat if you want to, and just use those 4 variables to directly, I guess 5 if you count omega, to directly calculate gamma. Then again, break it into the real part and the imaginary part, and you're definitely going to want to know how to do complex arithmetic on your calculator. If you haven't learned how to do it yet, it will definitely be worth your time to do so. Now, once you know the alpha and the beta, this alpha is going to be known as the attenuation constant. I probably don't need to write this because it appears later, but the attenuation constant, and beta is the phase constant. Alpha refers to the envelope. So if we have a decaying exponential, which is going to be the general form of our solution, there's going to be an envelope that the sinusoid is decaying, and it always just barely comes up and touches that envelope. Alpha controls how quickly it decays, and beta controls how quickly it oscillates while it's decaying. And so it's pretty remarkable that we can go from R hat, G hat, L hat, and C hat to alpha and beta, and so quickly find what the solution is going to look like. You can see here just what I mentioned, that the exponent, e to the minus alpha times z, and then the beta is going to determine how quickly it's oscillating in space. I should say this is in space for a particular t equals some snapshot in time. So that's the most general form of the solution. It has a component of the wave that's moving to the right and a component of the wave that's moving to the left, and the same really relationship exists between the voltage and the current. Okay, let's do one of these. I have a problem where there's an L hat, a C hat, an R hat, and a G hat. And I also know the frequency, 10 megahertz, and the initial amplitude is 5 volts. So that'll be equal to V1. And it is moving to the right. So since I know that it is moving to the right, that means that in this particular problem, and really in most of the problems we're going to be working with, the moving to the left components can be struck out. I'm gonna erase that, but because it's not generally true, but for this problem, it will be true. So let's start off by finding omega. Omega is 2 pi times f, which is 2 pi times 10 mega, that'll be my shorthand notation for 10 times 10 to the 6th. And that equals 6.28 times 10 to the 7th radians per second. I can then calculate y hat. Y hat is going to be equal to g hat plus j omega c hat, which is equal to 10 times 10 to the minus third, or 10 milli, plus j times 6.28 times 10 to the 7th, times 200 pico, which is 200 times 10 to the minus 12th, and that's equal to 0.01 plus j, hold on just a quick second, 0.0125. And that is in units of Siemens, because admittance has the units of 1 over ohms, which old school used to be called mhos, M-H-O, the ohm in reverse order. Now it's called Siemens, S-I-E-M-E-N-S. And then z hat is equal to r hat plus j omega L hat, and that is 10 to the minus 1 plus j times 6.28 times 10 to the 7th times 10 times 10 to the negative 9th. And that works out to be 0.1 plus j 0.628, and that is in units of ohms. And then gamma is the square root of z hat times y hat, and that is the square root of 0.01 plus j 0.0125 multiplied by 0.1 plus j 0.628. This is where having your calculator do complex arithmetic is very helpful. 0.0408 plus j 0.0925. So therefore alpha is 0.0408, beta is 0.0925. And it says, calculate and describe the voltage. Well, let's describe it. I left myself a little bit of space here. I know that it's going to be a decaying exponential, so I know that it's going to start at V1 is 5 volts. I know that it's going to decay downward. I know that it's going to oscillate, and it's going to start as a cosine, so it's going to start at the peak, and then it's going to go down, and it's going to oscillate like this. I don't really yet know how quickly that's going to oscillate, but I do know that V of z comma t is going to be equal to e to the minus alpha z times the cosine of omega t minus beta z. And this is equal to e to the minus, I'm sorry, there's a v1 in front there. So v1 is equal to 5. So this is 5 e to the minus 0.0408 z cosine of 6.28 times 10 to the 7th t minus 0.0925 z. So that's my final answer for what does this curve look like. But I can then, let's focus on the exponent part. This is e, so let me try this. 1 over 0.0408 is equal to 24.5. So this is e to the minus z over 24.5. And that means that it's not a time constant, but it is the decay constant, is that this is going to be, it's going to decay down to 1 over e a certain distance in, and that certain distance is going to be about 24.5 meters. So it will decay to 37% of its original value, so that would be 37% after 24.5 meters. So you could say that this is going to decay on the order of 25 meters or tens of meters would be another way to say it. How quickly will this decay? It'll decay over tens of meters. By the time you get to 100 meters, it's going to be e to the minus 4, which is a fraction of a percent. And then lambda is the wavelength, and that's going to be 2 pi divided by beta, which is 2 pi divided by 0.0925, which is 67.9, and that's going to be in meters, which means that one wavelength, which is the distance from here to here, so one wavelength is 67.9 meters. That's a pretty long wavelength. But it also means that we're not going to have very many wavelengths over the course before it's going to decay. You know, it's going to decay, and I realize now 24.5 meters should have been to the left of 69 meters, but just the way that I drew it, that didn't work out. I can tell you that it's not going to oscillate very many times, because a good rule of thumb is, you know, it's going to sort of be it's going to be the 24.5 and the 67.9 is going to give you an idea of how many times is it going to oscillate. Maybe 2 times before it effectively dies out. And so this is what the actual curve looks like. I plotted it using MATLAB. The dotted line represents the e to the minus alpha z, and this is the total solution v. And you can see that, yeah, it's oscillating, and it oscillates down and then back up again, but it is really pretty much almost died off by the time it's at about 1.5 oscillations. So if the numbers for the G hat, C hat, R hat, and L hat were different, this could oscillate hundreds of times before it died out, but the particular details of this one say that it oscillates about 1.5 to 2 times before it effectively dies out. So that's the voltage on a lossy transmission line. Now, there's another problem. So far what we've really been talking about is the fact that the signal is going to die off. We have now a solution. We understand how quickly it's going to die off. We can calculate that for any given transmission line, but there's a bigger problem. And that bigger problem is known as dispersion. So remember that we have a general form for the phase velocity. In the first part of the class, we're a little sloppy. We just call it velocity or propagation velocity, but now we need to get precise because there's going to be 2 velocities floating around. There's the phase velocity, and then there is the group velocity. But the phase velocity is the main one. So this is the main velocity that we've been talking about velocity for, oh gosh, 2/3 of the book now, and this is omega divided by beta. It used to be omega divided by k, but beta and k are kind of very similar to each other. K is lossless, so we haven't really mentioned that k was lossless because everything has been lossless up until now, whereas beta is for lossy. So beta fills the role of K as soon as we transition from lossless to lossy. So whereas this equation used to say V equals omega divided by K, now we're going to be more precise and say phase velocity, and that K almost even looks like a beta. It becomes omega over beta. But let's scroll back up again and remember that we already have an equation for beta. Beta is, if we come back up here, beta is the imaginary part. Beta is the imaginary part of gamma. So beta is the imaginary part of gamma. And we have this equation for gamma. So beta is the imaginary part of that big thing under the square root. And so that's what I've written here as this equation 28.19. But notice that there's an omega. There's two omegas floating around under that square root. And so there's going to be a couple of omegas floating around in the denominator of 28.18. And that means that taken together, those two equations show that the phase velocity is going to be a function of omega. So if you think about it, you've got a signal. Now I'm going to be in the frequency domain. So here I'm in frequency, or if you prefer omega, whichever you'd rather have. So there's going to be some sort of combination of a signal here, because it's never going to be just at a pure single sine wave. If you're going to transmit power or energy or information, it always has to be at more than one frequency. Well, maybe these higher frequencies are going to be, and I'm just going to be very generic about this, maybe the higher frequencies are going to be fast, and maybe the lower frequencies are going to be slow. That means that the higher frequencies are going to go, they're going to propagate down the line faster, and then the lower frequencies are going to propagate slower. But what started out as a nice tight square wave, which requires a perfect superposition of many frequencies, is going to become more of like a sort of a generic kind of mushed out sine wave or square wave. And then if it goes long enough, it's just eventually going to just become like something that's very difficult to even tell what the original signal was. That's because the velocities are propagating at different rates. Think about it this way, if let's imagine, this isn't the case, but let's imagine that a person's velocity of walking is proportional to their age. Maybe up until about age 30, that's correct. And let's imagine that you've got a family of 4, 2 parents and 2 kids, and they're going to be walking 100 meters. And their velocity doesn't vary that much, so they're going to pretty much get to the end at about the same time. But now let's imagine that same family of 4 is going to walk the Oregon Trail. So they're going to walk, 1,000 or 1,500 miles. And as they're progressing along that Oregon Trail, the parents are going to be walking much faster, and they're going to leave the children behind. And now we're in a world where this is just an analogy, but the family is going to be spread out. And whereas it used to be a nice, tight, compact family, now it's spread out, and basically the cohesion has been lost. That's what happens when there's a frequency dependence of velocity, that some of the wave components are going to go faster, some of them are going to get slower, and it turns out that when that happens, bad things happen. This is known as dispersion. And dispersion is when the velocity of propagation is a function of omega. Anytime that's the case, you're going to have dispersion. And when that's the case, then the faster components are going to arrive first. The slower components are going to arrive last. But they're going to be out of order. They're going to be out of phase. They're going to be interfering with each other. It's bad times. This is really not something that we want. We're observing that this occurs, but we are not a fan of it. And in the second half of today's chapter, we're going to talk about how to eliminate it. It turns out that this is really a problem, as I mentioned, when the transmission lines become especially long. When the telegraph was first invented, dispersion caused the signals to be unrecognizable if they were transmitted for more than a mile or so. A mile doesn't seem like very long, but it is long enough that this dispersion was causing a lot of problems. The only solution that they had was to set up a telegraph booth about once every mile. And as the telegram would be transmitted, there'd be a person in that booth who would receive it, write it down on a piece of paper, and then retransmit it to the next person who was a mile away, who was a mile away, who was a mile away. It's sort of like the bonfires in Lord of the Rings, where it's just going a certain distance and it has to hop and hop and hop and hop. And it turns out that that made them very slow because, rather than arriving instantaneously, they had to be copied and transmitted and copied and transmitted and copied and transmitted. They were error prone because people would make a mistake as they were receiving and transmitting the signals, and expensive. You had to pay these people, and you had to pay them extra to live out in the middle of nowhere and sit in a booth all day waiting for an incoming transmission to arrive. So this was bad times. This was not good. And at the end of the chapter, we're going to see how the hero of the story, who was a genius electrical engineer, fixed that problem. But we're not ready for that yet. Now, dispersion also has an interesting side effect. When multiple sinusoids of different frequencies interact with each other, their constructive and destructive interference makes it appear that the waves form groups. They form clusters of information. And I've tried to illustrate that in figure 28.3. I have here two frequencies. In the top half of the figure, there's a red frequency and a green frequency. And I'm going to show you this animation here in just a second. The red frequency is going to move more slowly than the green frequency. But the constructive and destructive interference between those means that the blue line on the bottom, which is simply the sum of V1 plus V2, see how that looks like there's little clusters or little groups of information? Those clusters are going to move at a different velocity than the phase velocity. So in the top half of this animation, you can see that I have two sine waves. Obviously, they have different wavelengths. And if you look carefully, they also have different velocities. The red wave is a longer wavelength, and the green wave has the shorter wavelength. The green wave is propagating more quickly. This is sort of representing the fact that there would be dispersion, or a difference in phase velocity based on the frequency of the signal. When you add the red wave and the green wave together, you get the blue wave on the bottom. And that blue wave, as you can see, does appear that there are clusters of information, clusters of signal that have been put together by the constructive and destructive interference of the waves. The blue wave has an envelope, which I've shown with the dotted black line there. And you can see that the blue dot, which is about halfway across now, the blue dot is showing the phase velocity. That is the velocity of a point of constant phase along the blue line. But you'll also see that the envelope is moving with a different velocity, and that's marked with the black dots. And so you can see now one of the black dots is just about to catch up to the blue dot, and that's showing that the black dots are moving more quickly than the blue dot is. And that means that the group velocity is higher than the phase velocity in this example. Now you can also have cases in which the group velocity would be lower or even negative of the phase velocity. In this case, I've kept it pretty simple and just shown that the group velocity is higher than the phase velocity. So now we see how dispersion, which is to say when different frequency components propagate at different velocities, leads to groups of signal, how it leads to a clustering of the signal into groups, and how the groups will propagate it at a velocity that's not necessarily the same as the phase velocity. It turns out that we have an equation that you can use to calculate the group velocity, but I remember when I was first studying this equation really bothered me because I didn't understand how to apply it or when to apply it. So I'm just going to tell you that you will not apply that equation. Here's the reason why you won't apply that equation. If there's group velocity, that means that you have dispersion. And dispersion means that you have a bad transmission line. That you don't want to have dispersion because it's essentially group velocity is like saying, oh, my system is performing poorly, it's misbehaving. And so I need to find a way to eliminate dispersion, which will therefore eliminate group velocity. There are two ways that we can eliminate dispersion. We can reduce the losses, so we have a nearly lossless line, or we can use what's called a distortionless line. And so let's talk about those two options. A nearly lossless line is one in which the lossy terms, R hat and G hat, remember that those are the new terms that we've introduced, if they're very small, then, and especially that will be the case if the transmission line is of good quality and big enough for the particular length of your transmission. Sorry about that extra period there. In this case, we can develop approximate equations that will represent the voltage and current. So we're about to enter into a world where we're approximating things. So I'll tell you when we transition from perfect to approximate. What we know is that we can factor out a square root of j omega L hat and a square and j omega C hat. We can factor that out of our equation for gamma, out of equation 28.15. Then I'm gonna look at this term right here, and I'm gonna FOIL that term. But when I do the first, outer, inner, last, notice that three of the terms are gonna stick around because they're gonna be first order terms. But there's gonna be a term that is R hat, G hat, divided by j omega L hat times j omega C hat. Well, if we know that r hat is pretty small and g hat is pretty small, then the product of r hat times g hat is really pretty small. So we're going to be able to essentially wipe out that fourth term and keep only the first three terms. So this is the first, I believe this is the inner, this will be the inner, and this is the outer. So I guess it's not FOI, it's FIO, but it's this L term that we canceled the L term. So now we also furthermore know that if x is relatively small, then mathematicians have proven that this expression is true. So we're going to apply 28.23 to 28.22, and we get 28.24. Then we're going to focus on just the real part of this equation. Now the real part of this equation is this term multiplied by this term, because the two j's are going to multiply together and give us a -1. Everything else is real. And the two j's giving us a -1, that -1 is going to cancel with this negative sign, so alpha turns out to be positive. We can rewrite alpha, and we end up with an expression where everything in alpha is independent of omega. Because it turns out that there are two ways that things can go badly. One of them is when we've talked about dispersion. Let me scroll back up here. Dispersion is when the velocity of propagation is a function of omega. But there's also another thing called distortion. Distortion is when alpha is a function of omega. And my analogy is about to get pretty brutal here, so I'm going to apologize in advance. But again, if you ever played that Oregon Trail game, let's imagine that the probability that a person is going to die, it depends on their age as well. So the younger people would be perhaps more likely to die than the older people. That's essentially what's happening here, is if we have a frequency range, maybe everything down here is more likely to be attenuated more. So it's going to be cut off more, and everything in the higher frequencies is going to be cut off less. So what we end up with is a signal that kind of used to be nice and smooth. Now we've got a lot more of the lower frequencies chopped off. Well, whether it is that the frequencies are being spread out by dispersion or whether they're being chopped off by distortion, neither one of those things is good. But it turns out that in the case of a nearly lossless line, that's not the case. That alpha is really just, it's a constant. If you look here at this equation for alpha, which I probably should have put a box around, that alpha has no dependence on omega. And so therefore attenuation is going to be constant across all frequencies. That prevents distortion. As I mentioned, distortion is when alpha is a function of omega. Distortion and dispersion sound so similar. That's why I'm trying to really illustrate the difference. We can also write an expression for beta. Let me go back up to the equation that we had up here. This equation that I've already marked up quite a lot. Let me take out some of those markings. If what I want is the imaginary part, then that's going to be just these components here. So beta is going to be omega times the square root of L hat times C hat, which is what I've written here. And then it's going to be approximately equal to that. And then if we take that equation, and remember that the phase velocity is equal to omega divided by beta. That's what equation 28.18 said. I'm going to take this, and I'm going to plug it in for beta here, and I get omega over omega times the square root of L hat times C hat. And therefore, the phase velocity is A, a constant, B, not dependent on frequency, and C, it's the same thing that we've already been seeing for phase velocity for quite some time. But the most important thing to see is that the phase velocity is not a function of omega. That means that all the frequencies are going to propagate at the same velocity. That means that there's going to be no dispersion, and because there's no dispersion, there will be no group velocity to deal with. So that means that if we had a nearly lossless line, we would be able to see that the behavior of the system would be vastly improved. So for the nearly lossless case, not only is attenuation constant and independent of frequency, but the phase constant, beta, is also linearly dependent on omega, so the phase velocity is also independent of frequency. So no distortion, no dispersion. Let's calculate alpha and beta using those approximate equations. So we just found that alpha is approximately equal to 1/2 times the square root of L hat C hat times R hat over L hat plus G hat over C hat. That's equal to 1/2, and I'm going to kind of be a little bit sloppy in my notation here. It's 10 nano So I'm just going to write 10n, which is 10 times 10 to the negative 9th, multiplied by 200 pico, which is 200 times 10 to the negative 12th, times 100 milli divided by 10 nano, plus 10 milli divided by 200 pico. Now, if you don't like being that sloppy, then I totally embrace and endorse you using the full equation here. What I end up with is 0.0424, and I should have mentioned before that the units on alpha are Napiers per meter. And when I do beta, I get beta to be approximately equal to omega times the square root of L hat times C hat, which is 6.28 times 10 to the 7th, multiplied by the square root of 10 nano, multiplied by 2, and this is equal to 0.088 radians per meter. So we can combine those together. Gamma is equal to alpha plus J times beta, and that is equal to 0.0424 plus J times 0.088, and that compares to gamma equals 0.0408 plus J 0.0925. That was our answer to 28.1. So if you look here, 0.0424 to 0.0408 and 0.088 to 0.0925, these are different by 4 to 5%. So not too bad, pretty good. And you know, we're in a place where we're talking about lossless, or we're talking about lossy versus nearly lossless. The G hat and this and the R G hat and this L hat. I'm sorry, try this again. The R hat and the G hat are pretty small, and so therefore we're pretty close to the nearly lossless case. Of course, to have a nearly lossless line, you're going to have to pay extra to have larger conductors, because larger conductors will reduce R hat. And you're going to need to have better insulators, or maybe thicker insulators, because that's going to be G hat. And G hat is going to go down. There'll be less leakage current if you have better insulators and if you use thicker insulators. So throwing money at the problem is one way to solve it. But in general, electrical and computer engineers usually like to throw math at the problem, because that leaves more money for raises. So let's talk about how to throw math at the problem. Distortionless lines. It turns out that there is a special case under which the line will be what's called distortionless. So a distortionless line requires that this be true. R hat over L hat equals G hat over C hat. Now you might say, I do not know where that equation came from, and to be honest, there's no way that I would have ever derived that equation either. But brilliant people in the 1850s didn't have Netflix and Hulu to distract them. They spent their entire lives looking at equations, and they figured this out, that if R hat over L hat equals G hat over C hat, then what we do is we take our equation for gamma, and notice that what I really did here was I replaced G hat by solving this equation for G hat, and then it went into here. So R hat times C hat over L hat. Then when I cross multiply this out, when I rearrange that expression, I get equation 28.32, where alpha then is the real part of gamma, and look how alpha is now independent of omega. It's just a constant. So that means that there'll be no distortion, because the attenuation constant is independent of frequency. So all frequency components are attenuated at the same rate, and therefore no distortion. The phase constant, beta, is the imaginary part. So if I look up here, what's the imaginary part of this? I have omega times L hat times the square root of C hat over L hat. And the L hat can come inside the square root, and then it becomes omega times L hat, omega times the square root of L hat times C hat. And when I plug this into my equation for phase velocity, so I'm just simply saying phase velocity is equal to omega over beta. That's a universal truth. I'm going to plug this in for beta, and therefore I get this. I guess you can't cross pages. And then I get omega times the square root of L hat C hat, and then the omegas cancel, and I'm left with not approximately equal, but precisely equal. And precisely equal means that if we have the special case of a distortionless line, then the phase velocity is also independent of the propagation, is also independent of the frequency. So if V sub p is not a function of omega, then that means that we're going to have a system that is not only distortionless, but also dispersionless. So there's no dispersion. Now you might ask yourself, how likely is it that we're going to get lucky enough to find that R hat over L hat equals G hat over C hat? And the answer is not very likely. I mean, some manufacturers today will manufacture transmission lines that offer that characteristic, but think about the 1850s. Think about when you're trying to figure out how to get rid of these little huts every mile along the telegraph line, and you have the lines installed, and they were not meant to satisfy this expression. So we have to figure out a solution to this. What we typically find is that instead of these being equal, we usually find that the left side is greater than the right side. So the first natural thing would be to think, oh, I need to reduce the left side. So let's make R hat go down. But to make R hat go down, again, you have to have larger conductors. You have to have better conductors. You have to throw a lot of money at the problem. But it turns out that there's a second option, and that is to make L hat go up. So if the denominator of the left side went up, then the left side would get smaller, and therefore we would no longer be unequal. I should erase that. We would go back to being equal. So we need to increase the inductance. We're going to increase the inductance by putting a little inductor, say every 100 meters or every 200 meters. And just by putting that little inductor, very precisely sized, every 100 meters, Oliver Heaviside was able to figure out how to eliminate all of those little huts. So instead of telegraph going a mile, now a telegraph can go 100 miles. So Oliver Heaviside, who's already appeared twice in this book, he was the genius electrical engineer who was already the only person who had starred in two historical perspectives, chapter 1 and chapter 14. You know, if a person says to you, oh, you're an electrical engineer, you must like Thomas Edison, you might say to them, no, I like Nikola Tesla. And if they say, oh, you like Nikola Tesla because it's cool, you say, no, I like Oliver Heaviside. Oliver Heaviside is the coolest of electrical engineers. So he was the person who figured out all you have to do is just add a little bit of inductance along the line, and when you add that inductance, then this equation is met. Then R hat over L hat equals G hat over C hat, which then means that you have neither distortion nor dispersion. So let's consider a lossy transmission line that has L hat 10 nanohenries per meter, C hat is 50 nanofarads per meter, R hat is 100 milliohms per meter, and G hat is 10 millisiemens per meter. We want to make this line distortionless. We're going to add an inductor every 100 meters. What value must that inductor have? So this is where you earn your big bucks, is by figuring out, and of course we're not working today with telegraph lines, but we do work with long distance telephone lines, and we do work with internet lines, and having dispersion or even distortion on an internet line is just nightmarish. So we want to be able to figure this out. So we know that we must have L hat over, oh, hold on, let me get the equation right. It was R hat over L hat. So R hat over L hat has to equal G hat over C hat. That means that I can calculate L hat. I'm going to call this the total L hat, which includes the original L hat plus the corrected L hat. This has to be equal to R hat times C hat divided by G hat. And that's going to be equal to 100 milli multiplied by 50 nano divided by 10 milli, and this works out to be 500 nano, and I'll make it complete, nanohenries per meter. And then the additional, so I'll say the additional compensator inductor needs to be 500 nanohenries per meter minus the original inductance, which was 10 nanohenries per meter. So that works out to be 490 nanohenries per meter. We need to multiply the original value by 50 to make this line be distortionless. So if we take what is L is going to be the L sub C hat times delta Z, and we got 490 nanohenries per meter, and we're going to do this once every 100 meters, so that means that this needs to be 49 microhenries. It's a pretty big inductor. It's going to take a little bit of coil of wire. It's going to take some time and some energy to go through and put one of those every 100 meters. But once you do that, you won't need those little people in the huts, and you won't need to retransmit the signal. You'll improve the quality, you'll improve the reliability, you'll improve the cost, you'll improve the speed, all of that just by adding these inductors. But of course, the secret is not adding the inductors. The secret is knowing how to add the inductors and how much inductance to add, and that all came from the math that Oliver Heaviside did. So let's see our summary. We have a lossy transmission line that includes a new term R and a new term G, and gamma, which is the overall propagation constant, can be calculated by combining those terms as shown. Gamma is a combination of the attenuation constant and the phase constant. We can find the overall solution to the line, which has a decaying exponential multiplied by a cosine, with a term moving to the right and a term moving back to the left. We know that the phase velocity is omega divided by beta, but if beta is a function of omega, then phase velocity can also be a function of omega. And that means dispersion. Dispersion means group velocity, and group velocity is bad times. That means that we're going to find that the signal is going to be ruined on its way to the destination. So if we have nearly lossless lines, we can eliminate that problem because they're both the phase velocity and the attenuation constant are both nearly independent of frequency. But the best solution is to ensure that the line is distortionless, which requires that this equation be true. And if you do that, typically by increasing L hat, then the attenuation constant and the phase velocity are both perfectly constant, and that means that you'll have neither distortion nor dispersion on your lines.